All right, let's do our homework together. 8-1, number 1. Don't give up, right? So we have a series. And it says approximate the sum of this alternating series with an error of less than or equal to 0.001. So we're going to plug in 1, and then 2, and then 3, and then so on, and then simplify it in terms of that. So it's 1 minus when I plug in 2, when I plug in, and the numerator is going to be 1 or negative 1, right? So we're just cubing 2, 3, and so on. So it's 1 over 27 minus 1 over 64, 1 over 25. And the question is, how do I know when to stop? So I don't even... So we don't really, you're going to have to figure out, okay, let's see. So at 1 over 9 cubed, I need to know what that answer is. Is that answer smaller than 0.001? That's what I'm looking at. So 1 over 9 cubed. And so that number is still bigger than 0.001. So if I want 1 over 10 cubed, that number is not small. It's equal to 0.001. So if I want to make it less than or equal to that, right, in terms of it. So that's where I stop, right there. And then I'd use my calculator, and the answer would be 0.902116. All right, number 2. If the first 4 terms are used to approximate this series, I have my question right here. Sometimes the font size is really small. Negative 1 to the n plus 1. There's your alternating. And then 2n cubed minus 1. And it says to find an upper bound for the remainder, for the first 4 terms. So the key is then the 5th term to find that upper bound. So for that, we're going to use the 5th term. So if I plug in the 5th term, it's positive 1. Plug in 5 cubed. You don't even need to simplify it. And that gives you the answer. So it's the next term. We call that the alternating series remainder. And there's your answer. It doesn't even matter to simplify it on your calculator. Number 3. Approximate e to the negative 1 with a 6-degree Maclaurin. That means it's centered at 0. And find an upper limit for the alternate series remainder. So I need to know the next term, right? So first of all, e to the negative 1 is a power series, elementary series that you should know. So we'll first do the first, how many? 6. So let's do the first 6. Two, 3, 4, 5, right? It's really 1, 2, 3, 4, 5. All right. For that. And that means the 7th one, there's the 6th, the 7th one, that would be your error approximation. So the alternating series remainder would be less than or equal to 1 over that. And that's fine. The next term. Number 4. How many terms of a Maclaurin polynomial are needed to approximate sine 1 with an error of less than 0.001? So we need to know our elementary for sine 1. So it's 1 subtract 1, and it's the odd numbers. The cosine's the even numbers. And then when do I know when to stop? So the next one is this one, 1 over 7. So what's 1 over 5 factorial? So when I look at that, that number is not smaller than 0.001. But the next one, 1 over 7 factorial, that number is smaller than 0.001. So then I know when to stop. So it stops there, and that is your answer right there. And the question was how many terms, right? So the answer is 3 terms. Okay, that's how many terms I used. The fourth term we don't need because it's the fourth term is smaller than 0.001. Number 5. How many terms of a Maclaurin again are needed to approximate sine 2? Okay, so how would that change in terms of it? So the first one's still going to be 1, but then it's going to be 2. And it's going to be 2. And we alternate with these odd ones. It's this one. So if I put this into my calculator, that number is still bigger than 0.001. This one is smaller. So how many terms I got? 1, 2, 3, 4, 5. So this one's 5 terms. And again, I keep going, and the number is that 0.001. As soon as that number is smaller than 0.001, that tells me how many terms to use. All right, number 6. If a Taylor Pauli, so that means it's not centered at 0, it's centered at 1, is used to approximate ln 2. So again, it's centered at 1, so it's like x minus 1 every time. So we're going to plug in 2 instead, so it's going to be 2 minus 1. And then again, it's going to be 2 minus 1 to the 2, and then alternate 2 minus 1 to the 3, and then alternate. It's going to be a lot. So 1,000 terms. So when you end at 1,000, because it's 1 over, 1 over, 1 over, right? So I understand the pattern now. So it's 1/2, 1/3, and so on. What number is going to be? So when it's 1 over 999, that number is bigger than 0.001. This is 0.001. So how many terms do we get to get there? So the answer is 1,000 terms. So that's understanding the pattern. 1 over, 1 over, 1 over, until we get to what we need. So again, 1 over 1,000 is 0.001. So that's where we would stop. And so there are 1,000 terms there. The next term is smaller than 0.001. All right, number 7. So if the fourth term is less than or equal to 4, find the Lagrange error bound to the third degree Taylor polynomial centered at x equals 1, used to approximate f at 2. So if it's less than or equal to 4, the Lagrange remainder, LR, Lagrange remainder, then we'll start with 4. And if it's a third degree Taylor centered at 1, then it's like x minus 1, right? So we plug in 2 to be 2 minus 1. And which term are we using? Third degree, so we need the next one after the third, that's 4. And there it is. And you don't have to simplify it. Number 8. So using the one from problem 7, third term here is 5. Find the range possibilities for f at 2. So if I simplified this, the 4's would cross. That would just be 6, right? 2 times 3. So this is just 1/6 when you simplify it. So in other words, you would add 1/6 and you would subtract 1/6. Oh, add on this side, obviously subtract on this side. So it's going to be bigger than this and smaller than this. This is that error approximation that you would use on both sides of 5. All right, number 9. The sixth term of 200 sine x, where x is equal to 0.5, with a 5th degree Taylor. So we're going to use the sixth one, right? The next one's centered at 0. So it's Maclaurin. So let's start with the 200. And then for sine, we're going to use sine of 0.5. So that's what that is. 200 sine of 0.5. And then we use that sixth term. The next term. Number 10. If we're going to break it down simple, right? It's the next term. If a 6th degree Taylor polynomial center is 0 used to approximate, find the Lagrange error bound for each of the following if the graph shown is a portion of the graph for the 7th. Interesting. So for A, we have 2, so we're using 2. And for x equals 3, so it would be the error be less than or equal to, so we use that y value 2, and then it's going to be 3, because it's centered at 0, so this is 3 to the exponent 7 over 7 factorial. Then that's A. B, the error. So at 3 would be right here. No. Which one? Yeah, right here at 4. Same thing. And then the error. What's the next one? B0? No, 3. So you find the maximum value on the graph. So the maximum value here, the maximum value in that part is 3. And then there's your error approximation. All right, number 11. All right, assuming the functions from 10, problem 10 is represented by alternating series, which of the 3 answers would be the same as an alternating series bound? So the one that would be the next term, right? And so that answer would be C if it was alternating. That's because the max value is centered at 0 compared to the other ones. All right, number 12. So f at x equals e to the negative 2x. And it's approximated by 1 minus 2x plus 2x squared minus 4/3 x cubed. It's an alternating series. Use the area bound to positive for this approximation has an error of less than or equal to 27 over 8. So for x, the next term in this one would be 2/3 x to the 4th. And that 2/3 x to the 4th would have to be less than 27 over 8. So if I multiply by the reciprocal, right? Yeah, x to the 4th would be 81 over 16. And then the 4th root of that would be 3 over 4. No, 3 over 2. And there would be the answer. All right, number 13. F at x equals ln x and centered at 1. Write a Taylor poly 4 terms deep. All right, so if it's centered at 1, then we start with x minus 1 for ln. It alternates. We just count up. So 2 alternates, 3 alternates. And I said how many terms? 4. So 1, 2, 3, 4. That's good right there. Then for b, it says write a power series using some notation for it. So the power series, it alternates, and it's x minus 1 to the n over n. It's that series. Part C. Approximate f at 1.3 using the 4th term at 1.3. So just plug in 0.3 in here. In terms of x minus 1, it's now 0.3. So it'd be 0.3 minus 0.3 plus 0.3 minus 0.3. And if you use your calculator, it'd be about 0.261975. Part D, it says, what is actually right? Ln 1.3. Find the actual value. So use your calculator and the approximate value just with you could 0.26236. So you can see how close it is. Part E. It says find the Lagrange error of that to 4 terms. So again, we're thinking of the next term when we do that. So we want to find the derivative. So it's 1 over x, or it's x to the negative 1. So the derivative of ln x is 1 over x, or x to the negative 1. That means the next derivative is negative x negative 2. The next derivative is positive 2, negative 3. The next derivative is negative 6, negative 4. The next derivative would be positive 24 to the negative 5. So the max value, using the 5th one, be using 24. So from 1 to 1.3, it's centered at x equals 1. So if I plug in 1 to any exponent, the answer is just 24. So the 5th term, if you plug in 1, the answer is 24. So that's what I would use for the Lagrange error methods. So I'd start with 24, and then I'd use 0.3. Remember, we're centered at 1, so 1 take away 1.3 is 0.3. So it's 0.3 to the 5 over 5 factorial. Obviously, using the alternating series remainder would be much easier because you're just using the next term rather than doing this. What does F say? Find the number of terms from the Taylor-Pauli needed to approximate 1.3 with an error of less than 0.03. So the fourth term would be this. The fifth term would be 0.3 to the 5 over 5, and that answer is smaller than 0.01. So it would be 4 terms would be the answer. So you keep going until the answer is smaller than 0.001. All right, that's 13. 14. It says find an upper limit for the error when the Taylor-Pauli is used to approximate sine x centered at x equals 0.5. So it would be the next term, so it would be the fifth one. So the alternating series there would be 0.5 to the 5 over 5 factorial. And that's because that answer is 0.00026, which is less than 0.001. All right, number 15. So let f at x be a function whose Taylor series converges for all x. What is the minimum number of Taylor series centered at x equals 1 necessary to approximate f at 1.2 with an error less of 0.00001? So we're going to take 0.2 to the exponent n plus that over n plus 1 factorial. That has to be less than or equal to 0.00001. So we're trying to figure out what value for n would work. And if I plug in 4 and use my calculator, that answers 0.00, there's 40666. That's too big. So the next one would be 0.2 to the 5. I'm sorry. This one works. Sorry. If you try 3, it's too big. This is 3. So if n equals 3, this is what it would look like. If n equaled 4, so if you add 1, 3 plus, this is to the 4. This is to the 4. This one is to the 5. You add 1, right? And this answer works. Why does it work? Because it's smaller than what I'm looking for. So this means how many terms then? 5 terms. All right, number 16. 16, you have a table of values. It says calculators allowed. Let h be a function having derivatives of all orders that are selected for h, and its first 4 derivatives are indicated in the table. above. Write the first degree Taylor polynomial. So I'm going to use the values that I see to create that with the derivatives. For x equals 2, so it's 3 plus the derivative is 4, x minus 2. So those are two terms right there. And then you plug in 1.9. I give you an answer of 2.6. For part B, write the third degree. So this is first degree. Write the third degree. Let's start the same way. No, what's the next? Sorry. The next derivative is it's 3, then 4, then 5. Sorry. The next derivative is 6. Again, what degree we're going to? Third degree, right? So we can end there, right? Degree of 3. Part C. Assuming the fourth derivative of h is a positive increasing function, use the Lagrange error bound to show that the third degree, which we have for h, about x equals 2, approximates 1 point with an error of less than 3 times 10 to the negative 5. So that means you move the decimal way over 0.00000. So for the Lagrange error method, the number to begin with, 7. Then it would be 1.9, take away 2. So again, we're using the next term. So the error would be the next term. So it would be 7 would be the next one. That's the derivative of the next one. Then 1.9 times 2, and then it would be to the exponent 4 over 4. And that would give you the error, the next term after. So the derivative, and then 1.9 take away 2, because that's what x value is, and then to the exponent 4 divided by 4. All right, number 17. Going to write it calculus friendly right away. So take the derivative. Right? Is it plus? Positive times is negative. Haha. And then take the derivative again. So a negative times a negative times a negative, that's where it comes in. And then subtract. And you did it. Okay, number 18. Find the points where the line's tangent. So we have an equation. Tangent derivative is parallel to the graph of this. So if I solve for y, the slope here is 1. So we need to make it equal to the slope, which is 1. So the derivative is x squared minus 2x plus 1. And then I'm going to make it equal to 1 and then solve it. So subtract 1 to both sides. It's 0. Factor it. So the two answers I get are 0 and 2. And then if I need the point, you'd plug 0 in here. Well, that answer is 3. I'm going to help you with the second one. If you plug in 2 and get the answer, I just can't tell you. It's 11 over 3. Don't want you to stress out about that one. Number 19. Integration. We're going to separate this. I can't take the factor at the bottom, so I have to go a different method. So the first one's going to be arctangent, where a is the square root of 9, u is the square root of t squared, and then the derivative. So we need a 3 over 1, so it's 3. And then for arc, it's 1 over a, which is 1/3. That's going to be 1. It's fine. Arctangent u over a. So there's the first one. Minus. All right, the derivative here is 2t, but it was a 4. So 4 over 2 makes it 2. It's a logarithm. And then plus c. All right, number 20. Integrate arc sine over x minus 2 over the square root of 4 minus x squared dx. Let's make this look right so you can see it. I just looked at the answer quick to make sure I knew what I was doing. Mr. G Math, right? Still learning. So think of this to the exponent 1. The derivative here, in terms of it, it should be 1/2, right? So we need a 2 in front, or 1/2 in front. So this is actually the hook for this in terms of it, because the derivative matches. Long story short, just going to add 1 to the exponent and divide. Plus c. All right, 21. Integrate the square root of x minus 1 over x. So we're going to do some work here. So we're going to actually square and then get x by itself and then that. And then we're going to go back in here. So it says u over u squared plus 1. Dx is 2 du. Oh, it's 2u du. So this ends up being 2u squared du. Now the degrees match, so we have to divide. That's 2. Subtract, the remainder is negative 2. So come back here again. So now it's 2 minus 2 over u squared plus 1. This is arctan. So we have a 2, it should be a 1, so we just put a 2 in front. So this is 2u minus 2 in front, arctan u over a, which is 1, so this is u, plus c, and then put u back in, which is the square root of x minus 1. And you did it. A little U substitution, inverse trig. Pretty good. Pretty good. 22. We're almost there. Find a general solution of this. So we want the y's on one side. So first I'm going to combine like terms. So bring that and add 2y, subtract dy, and then divide out or factor out. And then divide. All right, now it's separated. Now we can integrate it. It's a logarithm. This is ln. This can be an exponent there, and then the logarithms can undo each other. So it's just y equals t minus 1 squared. All right, 23. The rate of growth of bacteria is proportional to the number of bacterial present. So it's this equation. Originally there are 2,000 after 3 days. Solve for k with your calculator. You get approximately 0.458145. Oh, we don't know this one here. We have this. We have this. 5,000 after 5 days. We have, and then we can solve for that. 2 equations, 2 unknowns. And this is what you get, k to equal. Part B, the number of bacteria originally in there. So we have 2,000 equaling C, E to this growth rate. After 3. And then solve for C with your calculator. You get about 505 or 506 for the answer. So if you use 505 E to the growth rate, after 12 days, approximately there's 123,000, so 300 using your calculator in terms of how many there are. All right, 24. I'm losing my pages here. All right. My class is going to start in a moment. So I'm going to do 24, 5, and 6 on a second video. I almost got there. So quick. All right, Mr. D Math over and out. Good job not giving up and trying your best. Till next time.